Welcome! So in this video we are going to run through some more u-substitution examples. So often it takes some work to see where the u and the du are in the integral. So it might not be written super clearly right away, and we might have to take a second to figure out where the u is and where the du is going to be. Or the integral might actually need some manipulation in order to see what's going on. So we might need to manipulate the integral a little bit. Let me show you some examples of what this looks like. Let's say we're taking the integral of x squared times e to the x cubed dx. Okay, so why don't you pause for a second and see if you can figure out what you think u should be for our substitution, and then find du as well. So take a second, see what you can figure out, and then we'll do it together. So for picking out my u and my du, I'm not immediately seeing that one of these items is the derivative of the other one, but I'm noticing that x cubed is something to the third power, and I have an x squared out front that has a power decreased by 1. So it's a good guess that u is equal to x cubed, and then du is going to be equal to 3x squared dx. So again, I'd start with my u is equal to x cubed, and I take its derivative. The derivative of u is 3x squared dx. So I wasn't given a 3x squared in my original integral, but I can do some multiplying to make this happen. So I'm going to insert a 1/3 times 3, because when we do this, this is really like multiplying by 1, and put it into my integral. Now I can factor that 1/3 out of the integral, and I have 1/3 times the integral of 3x squared e to the x cubed dx. And now I can see my substitution a little more clearly. So 3x squared dx is my du, and x cubed is my u. So I'm left with 1/3 times the integral e to the u du. So what I needed to do here was just put in that 3 in order to make the substitution a little easier, and now I have something in terms of u, and I can take the integral. So the antiderivative of e to the u is just e to the u, so I'm left with 1/3 e to the u plus c, and I want to substitute back in for x, so I'm getting 1/3 e to the x cubed plus c. And this is my antiderivative, or the solution to my indefinite integral. So for my next example, let's do the integral of 20x to the 4th divided by the quantity 2x to the 5th minus 7 cubed dx. So with respect to x. Why don't you take a second and pause, see if you can figure out what u should be, what du will then be, and you can try this as far as you can get on your own, and then we'll come back and do it together. Okay. So looking at this, I have quite a few exponents going on. I have something to the 4th power, I have something to the 5th power, and then I have a whole quantity being cubed. So remember, u is like the inside function that corresponds to the chain rule. So when I see that something cubed, I'm thinking that u needs to be that something. It also makes sense that u should be 2x to the 5th minus 7, because when we take its derivative, we're going to get an x to the 4th, which will hopefully correspond with what we have in the numerator. So let's let u equals 2x to the 5th minus 7, and then taking the derivative of u, I'm getting 10x to the 4th dx. So I don't necessarily have a 10x to the 4th in my numerator, but we can just do a little rewriting in order to make that happen. So 20 is 2 times 10, so I'm going to rewrite that as 2 times 10x to the 4th. So now it might be a little easier to see that I have that 10x to the 4th dx that I can replace with du, and in the denominator I have my u cubed. So I'm left with the integral of 2 over u cubed du. Alright, now I just have to compute this integral, so I'm going to factor the 2 out of my integral, and then rewrite 1 over u cubed as u to the negative 3. Then when I do the antiderivative, I add 1 to that exponent, so I'm getting u to the negative 2, and I divide by that exponent. 1 over negative 2 u to the negative 2, and don't forget my plus c. So the 2's will cancel, and so I have negative u to the negative 2 plus c, which I can make the exponent positive by moving it to the denominator, so I have negative 1 over u squared plus c. And my last step is just to replace u with what we substituted it for. So I'm getting negative 1 over 2x to the 5th plus 7 squared plus c. Okay, so in this problem we just had 2 we needed to factor out in order to get the 10x to the 4th that we were looking for. There's also a slightly different way to do this, and I'll show it to you at the end for both this example and the one before it. So as long as you follow your substitution properly, you will be good to go, and I'll show you a slightly different way to do it when we wrap up the video. Okay, let's do another example. So let's do the integral of cosine cubed theta times sine theta d theta. So here I'm integrating with respect to theta. Let's take a second and see if you can figure out what you think u should be and what you think du is based on that u, and you can go ahead and do as much of the problem as you'd like at this point. Okay, so what helps me is I like to take that cubed on the cosine and kind of write it outside the parentheses. So I really have cosine theta cubed times sine theta d theta. So here, sine and cosine, their derivatives sort of go together, like the derivative of sine is cosine and the derivative of cosine is negative sine. So there's not an obvious way to choose if one should be u and one is the du, but I'm noticing that I have this something cubed. And this something cubed is going to involve chain rule with a derivative sense, so I'm going to choose that cosine as my inside function here. I'm letting u equal to cosine theta. Then the derivative of u is negative sine theta d theta, and so what I'm missing here is just that negative sign. So my integral doesn't have a negative, but I do have the sine theta d theta. So to get myself that negative, I'm going to put a negative on the outside of the integral, and then put a negative on the inside of the integral. This is like a negative times a negative is a positive, so I can just put in these two negatives in this way. Then I have my negative sine theta d theta that I'm needing, and I can rewrite this whole integral as negative u cubed du, with that negative outside the integral. You could put it inside if you want, it doesn't matter either way. Now I have something I can integrate with respect to u. I add 1 to the exponent, I'm getting u to the 4th, and I have 1/4 as the counteraction to that. So I'm getting negative 1/4 u to the 4th plus c as my antiderivative. And to finish this off, I just need to substitute back in for u. So I'm going to have cosine of theta as my u, and I'm left with negative 1/4 cosine to the 4th theta plus c as my final solution. So here we just needed a negative. I wanted to show you what that looks like and how we can put it in. Okay, let's go through one more example, and this one's going to be just a little more complicated, and I'm going to show you a couple different ways we can tackle it. So let's do the integral of x to the 6th minus 2x, all divided by x to the 7th minus 7x squared, and this is with respect to x. So why don't you try to figure out what the u should be and what the du should be, and maybe see what you can do about making this work so that we can solve the antiderivative. Okay, so I'm seeing that we have something to the 7th power and something to the 6th power. So I'm thinking that denominator is going to need to be our u, because when we take its derivative, we're going to get the x to the 6th power that we need. So I'm going to let u be x to the 7th minus 7x squared, and then see what the derivative is. So just as a note, if you're working on a u-sub problem and you try a u thing and it doesn't work, like you pick a u substitution and it doesn't seem to be working properly, or the derivative when you find it isn't present, that's okay, just like try a different thing. Sometimes you'll have to just try a couple out in order to get more fluent and more used to knowing which u to pick. So here I'm going to take the derivative of u. I'm getting 7x to the 6th minus 14x dx. And I need to figure out where this is in my integral. So I'm sort of close. I see the x to the 6th and the x, but my coefficients are wrong. So what we need to do is make those coefficients on the x to the 6th minus 2x work for us, because we have 7x to the 6th minus 14x. So there are a couple ways to do this. I'm just going to show you two methods, just in case one of the methods makes more sense to you than the other one. I find that sometimes the way I do these types of integrals with u-sub isn't the way other people do it, so I just want to show you some options so you can try it whatever way it works for you. Okay, so what I'm going to do is that I notice that the numerator, x to the 6th minus 2x, if I was to multiply that by 7, I'd get the du that I want. So I'd get 7x to the 6th minus 14x, which is the du I'm aiming for. So I'm going to multiply the numerator by 7, and to counteract that, I then need to multiply by 1/7. So this is like a fancy way of multiplying by 1. Then I'm getting 7x to the 6th minus 14x in the numerator, and x to the 7th minus 7x squared in the denominator, with that 1/7 there still. So now I'm seeing that I have my du and my u, and I can factor that 1/7 out of the integral. So I'm left with 1/7 times the integral of 1 over u du. So I've manipulated this by multiplying by the 1/7 and the 7 in order to get what I needed. Now I can find the antiderivative. So the antiderivative of 1 over u is the natural log of absolute value of u. So I'm getting 1/7 natural log of absolute value of u plus c. And to wrap it up, I just need to substitute back in for u. So u is equal to x to the 7th minus 7x squared, and this gives me my final solution. Okay, so this method involved us multiplying by the 1/7 and the 7, but there's a slightly different way we can do this if we'd like. So let me show you what that looks like. Instead of rewriting the integral, we are going to rewrite du. So this means that we are going to manipulate du in order to be something new that we can then substitute in. Let me show you what it looks like. So here, I'm going to just factor out a 7 from my statement of du. So I now have that du is equal to 7 times the quantity x to the 6th minus 2x dx. This x to the 6th minus 2x dx, that's what I have in my integral. So I'm going to divide the 7 over to the other side in order to just keep on the right-hand side what I have in the integral. So I'm getting that 1/7 du is equal to x to the 6th minus 2x dx. Now I can evaluate my integral using this information. So I'm going to rewrite our starting integral as taking the numerator outside of that fraction. So I have 1 over x to the 7th minus 7x squared times x to the 6th minus 2x dx. Now, that x to the 6th minus 2x dx, I have just written that that is equal to 1/7 du. So I'm going to replace it with 1/7 du, and then do my regular substitution for u as well. So I'm getting the integral of 1 over u times 1 over 7 du. And this is going to look really similar to what we did in method 1. I can now factor out that 1 over 7th, and I'm just doing the integral of 1 over u du, which is the natural log of absolute value of u, and I'm left with my final solution when I finish the substitution back in of 1/7 natural log of the absolute value of x to the 7th minus 7x squared plus c. Okay, so the second method got us the same answer. It just involved manipulating the du and then substituting that in rather than manipulating the integral. So I find some people like this better. They like to try to manipulate the du instead of the integral. It just is easier. They like doing that better. So it's really up to you if you like that more. Truthfully, I switch between the methods depending on the problem. Sometimes it's easier for me to just do the first method because I see really quickly what needs to happen. and other times I like to manipulate the substitution in order to get a little more information or to figure out what I'm supposed to do. So we actually could have used this second method on our first two example problems. I'm going to just return to those really quick and show you what that would have looked like instead. So on our first example, we were doing the integral of x squared times e to the x cubed dx, and we had a u as x cubed and our du as 3x squared dx. So here you might notice in the problem, I have an x squared dx. I'd really like if I just knew what that was. So you could divide the du equation by 3, and so you're getting that 1/3 du is equal to x squared dx. Then in your integral, you can just replace that whole x squared dx with 1/3 du, and then solve the integral that way. So this might be easier for you than doing the trick we did with multiplying by the version of 1. Maybe you just want to manipulate the du in order to get something to substitute in. We get the same answer, and it's sort of a cool way to do it. Okay, let's try it with our other example. This is the second example we did. So we had the integral of 20x to the fourth over the quantity 2x to the fifth minus 7 cubed. And so here, on our du equation, 10x to the fourth dx, you might just notice, oh, if I multiplied this by 2, I would get the numerator that I have in my integral. So when we do 2 times du, I'm getting 20x to the fourth dx, and now I can replace that in my integral. So 20x to the fourth dx now becomes 2 du, and I have an integral that's entirely in terms of u that I can solve. So this is just another way to do it, and it might be faster for you. You do what makes most sense and what gets you to the solution. Okay, hopefully that gave you a good sense for how we do u-substitution problems and how they can get a little more complex. Thanks so much for watching, and I will talk to you in the next one.